Welcome all. So this is our webinar on stable diffusion, extensions, also Dreambooth and Controlnet, management. So we have Mitadru Datta here, an AI researcher with CellStrat AI Lab, and also a researcher at IIT Kharagpur. So Mitadru, are you ready?
Yes, sir.
Over to you. Just do a 1 minute quick overview of what is a diffusion model, and then you can begin the part 3 of this. And if anybody has a question, feel free to send in chat, or you can speak your question as well. Let's keep it
Okay.
really interactive. So, Mitadru, over to you.
Okay, sure. So today is the third webinar. So I'm giving you a small, like a quick recap of what we actually did. And like today's webinar can also be an hands-on session for using Controlnet and Dreambooth. So, so stable diffusion is something basically a text to image converter or image to image converter. So basically most of the AI art which you see nowadays are made from this. So this basically follows a forward process which happens by noising our images at different timestamp, and then we collect samples which may be close to complete noise or maybe at some different timestamp, and then we feed into our unit architecture model which basically predicts the noise, and then at the same time the backward process also happens by which we subtract the noise. Some of the mathematical details we had talked about, and this is the complete flow chart. So first the encoder converts the observed variables to latent variables, then we have the forward diffusion process, then the denoising unit which produces the noise subtracts it in the forward diffusion process, and our decoder then converts the final latent variable into the predicted observed variables. So in all these process, we also have some attention modules. We have some positional timestamp encoding, about whose details we have talked about in webinar 2. So webinar 2 was basically based on the backward process. The first webinar was the forward process, and we had also talked about what there is actually no particular loss function in this stable diffusion. So what we are actually maximizing is a maximum log likelihood loss. So we are basically pushing our data away from the data manifold and just going all the way back to the data manifold, so that our something we call as variational lower bound, we are going to maximize that lower bound, and we can land into different spaces of the data manifold every time we run the program. And this is basically the reason of why we see, due to this inequality, why we see is that every time we run the diffusion model, it may give us different output, but relevant output. So yeah, that's what was the backward process. We are to keep a track of what is going in and out of the neural network model. We use time step encoding, which uses sine and cosine positioning. Yeah, so just a second, I will just connect the charger to my laptop.
So folks, from previous 2 webinars, Mitadru had presented concept of a diffusion model, which basically involves training a neural network, which goes from image to noise, and then training a backward diffusion process, which trains the a different neural network going from noise to image, right? So Mitadru, one follow-on question from one of the Sunday webinars was the loss minimization in the forward diffusion and reverse diffusion. Is it an integrated loss minimization similar to the cumulative loss minimization in a GAN for generator discriminator, or the loss minimization of forward diffusion and backward diffusion is a separate process?
So actually, we are not minimizing in our forward process. We are just denoising we are just adding noise until we get a complete Gaussian noise, and then we are collecting noisy samples from different timestamp and feeding it to our neural network model. So in the forward process, we are not actually looking for maximizing anything.
Are we minimizing the loss or maximizing likelihood probability? Any
Yeah,
of those two things?
that actually happens in the backward process. So in the backward process, after pushing our data from away from the data manifold, like we get noise. After getting noise, we are trying to push back to into the data manifold, such that we are getting some combinations of images. Uh, so basically, what happens is that there is no, like, we cannot write any particular loss function. All we can say is that our while coming back into our data manifold, we should not have means we should have we can be greater than a particular value. Our path to the data manifold back to the data manifold can be greater than a particular value, that which we called as variational lower bound. So there is no particular loss function, but the maximum log likelihood loss, that we are just making sure it should be greater than a particular uh, inequality loss.
Got it.
So
So you
like
decide a threshold and you want to the log likelihood loss, you want to exceed the threshold. Okay.
yeah, and what we can do is we can maximize the threshold.
Right. So
So
if I were to
that
take negative of that, that would become negative log likelihood loss minimization, similar to logistic regression. But
yeah, that's another
keeping
term.
it positive, so it's a maximum likelihood
Uh,
maximization of the MLE. Yes, got it. So it's
yes.
somewhat similar to the logistic regression.
Yeah, like
So it is
uh,
still loss is still involved. It's just called log likelihood loss, and the negative of that would be maximization.
yeah, like the lower bound we are actually maximizing, not the exact function.
Got it.
So yeah.
Got it.
So we also talked about this positional timestamp encoding, which formed our last portion of last webinar, and we also talked about some extensions, some applications like infinite zoom in, zoom out, and like using it on something. Google Maps can improve that. We also talked about in painting, how that can be done by applying a mask and completing unfinished drawing and stuffs like some cool stuffs like these mind reading and all. Like from the brain waves, we can just from the brain fMRI signals, we can use SD to see what the person is actually thinking. And you might be knowing this quite famous application of the fashion industry. And medical imaging, we also saw stuffs regarding that. So I showed you a demo of uh, how like how to approach that SD by using PyTorch from scratch. So yeah, today we will not really do things from scratch, because like we have a lot to do. So we would just get an overview and an understanding of how we can actually use something which has already been made by some companies in their GitHub repository, like Automatic1111. So Automatic1111 is basically a GitHub repository from which we can use the various stable diffusion extensions. So yeah, let us just start. So a minor motivation before starting. I got this in one of the LinkedIn posts. So even so there is something known as deepagency.com. You can go and check it out. So they are basically giving their AI generated models to hire. So the models which you are seeing here, these two models actually do not exist, but but like they have been produced with stable diffusion, and then they like I saw a post like this, that this is insane, bye-bye to the modeling industry, and could AI kill the $85 billion a year photography industry? Or maybe in future we might also see the entire movie is made by AI characters, so you don't really have to pay those actors, and maybe some AI characters are becoming famous, which would look like humans. So yeah, that's also possible. So how to preserve the characters is the main essence behind Dreambooth, which we will study today. Try to understand today, and if time remains, I will also try to run the code for Dreambooth. So it takes a lot of time to run that code, and after running the Controlnet code only, I can show Dreambooth. So let us just get started quickly. So what is Automatic 1111? It is basically a stable diffusion web user interface, which is the main graphical user interface for advanced users. You don't have to write the code every time, or we can in a collab notebook, we can just clone these codes there, and we can just use that ready-made. So like it actually lacks proper documentation, which makes it like not so easy to use. So let us just see how we can do that.
So, yeah, friends, please feel free to ask question because it's a very complex topic, and this is third webinar actually in this series. So, if you have any questions, do ask because it is quite complex, and we all want to develop expertise in this, right? So, please do ask.
Okay, so we will see the step-by-step procedure for running Automatic 1111 on local machine. First, we are trying to run on local machine, since I lack some proper GPU. So I can run and show it, but like the final page would appear, but the complete thing will not run. But when I will be using something known as radio interface, which I will tell you, for Controlnet, you can see quite good results with that. So that's actually not local server. So first let us see on our local machine how to apply Automatic 1111. So what we can do is we can we first thing, you need to make sure that you have these requirements, which is Windows 11 or 10, or also a GPU with at least 8 GB of VRAM. So 8 GB is really preferred. I will tell you why, because lower RAM, even with 8 GB, it takes a lot of time actually. So at least 25 GB of local disk space should also be there. So what you can do is that, so I'm just closing the presentation mode because I may be requiring to go out of this again and again. You can download this zip file from Automatic 1111, or just use this. So what you can do is Automatic 1111 stable diffusion, and it would be nice if you do along with me. So you can just press this download zip. I have already downloaded that, and then you will get something to extract, since it is a zip. And then so now you also need to make sure that you have Python 3.11, because it, and like in a Python to the path. So I think that should be there by default. If you're using something like VS Code and initial setups you did correctly, then it should work without much proper tampering, without any tampering. So after extracting, what you would get is something like this folder. So I would just go through the folder once, how it should look after
Can you
extract.
share the link in the chat where to download?
Okay. So you can download the zip from here, extract that, and save it some folder. Let's say let it be stable diffusion WebGUI master. So this is that entire GitHub repository. So once you get all these files, you can just go and analyze that one by one. Let's see. Suppose we want to use some particular extension, we can put our extension here, and here are some built-in extension also, which you can use ready-made if you have GPU. And there would also be in this model section, if you go to stable diffusion, so you can put checkpoint files here. So what exactly is checkpoint files? After we train a model, so that we don't have to train it again and again, we save it in something known as checkpoint file. I hope you would be knowing that. So this contains all the weights, training weights basically. So this was not their default, so I will show how to bring these two files. At first, you should see only this text document, which says put stable diffusion checkpoints there. So let us see how to bring those checkpoints. So place the extension folder. So inside this folder, if you want to test any extension like Controlnet or Dreambooth, you can just place it here. So this way, you even in your local machine you can run for the Dreambooth or the Controlnet, and you can follow this link, which I will also paste in the chat box now. So there is a checkpoint file of SD 2.0. So actually, you can also use SD 2.0. I am giving you a checkpoint, ready-made checkpoint. This is, you can just use this checkpoint. So it will take time to download. It is 4.9 GB. You can click here, you will get this page, and you can just click here to download that. So you can check the download the checkpoint file, and then you will also, there is also an UML file associated with this checkpoint, whose link also I'm giving. This is the UML file. So this after like fidgeting a little bit with the Hugging Face library, you can obtain these all checkpoints and their corresponding UML documents. So UML text file, you can just like press Ctrl+S and you can just save it. It will get saved as a text file. So from that browser only you can do that. So one thing which you need to do is that after downloading this checkpoint file, you can open this UML file link. We can save this by pressing Ctrl+S, and what you need to do is to make sure that this checkpoint file and this UML file has the same name. You have to rename this same as the checkpoint file. Now this should be .uml, right? But this is .uml. The name is .uml, but as you can see, the save as type is text file. So you will also get something known as online text to UML file converter. So you can use that. So I have kept this ready so that this is text to online text to UML converter. Using this, I told you can save this UML as a text file by pressing Ctrl+S. You can just upload that text file here and download the UML file, and then you might you should rename the UML file same as your checkpoint file. So if you are doing along, it would be quite easy to follow.
Is anybody doing hands-on or just watching Mitadru do it?
Giving a try.
Okay, sure.
4.9.
Yeah, I know there are a lot of steps, so it's kind of hard to do it so quickly.
Yeah,
But that's
because
fine.
4.9 GB takes time to download. That's
Yes, yes.
Yeah, that would take some time.
So some of you are trying to do. That's nice. Okay.
Yeah. So meanwhile, it gets downloaded. As I told you, like we can navigate to the models and then stable diffusion. inside this, we need to paste our both checkpoint and your UML file. So as you can see, same thing inside models, stable diffusion. These two files have the same name, and this, like, one thing which can be quite confusing here is that at first, like as I was doing it for the first time, it was showing .uml, but here it was showing text file. So please look into that. This should also be UML source file. So that conversion you can do using that website, online text to UML converter. So this might take some of your time. So now what you can do is that you can run this batch file if you are on Windows, or run this. You will also get some similar WebGUI user sh file also you can get for Linux interface. Actually, this Linux interface has some problem with path and all, so I am just doing it on Windows. So here you can see there is this WebGUI user Windows batch file. So all you need to do is double click this. Okay. So it should execute automatically. Let's see. Yeah, in the command prompt, it's running. So just to see that, so since this also gives a check of whether our system is having GPU or not. So my system is not having GPU, dedicated GPU. In fact, mine is NVIDIA, so not dedicated GPU. So you can skip this torch CUDA test. So what you can do for that is you can open with something like VS Code, and then you can just, let's say, open it with VS Code. Or some other, maybe Python. And what you can do is add a command line argument. So there was a command line argument. So this was not there. This was blank at first. I had placed this argument, skip torch CUDA test. So it will help you at least at it, even if it doesn't run at final, but it will just let you use the interface even if you are not having a GPU. So you can do this. This is optional. So let's see what is the progress. Yeah. So we get this on our command prompt, and running on, you can see it is written running on Rocker URL. So we can copy paste this link on any browser. I am using Edge. So I will just copy paste this link. Let's see. This is a local machine. You can see the interfaces here. Here you can add the checkpoint files. Any extension you are training, and you will get the weights correspondingly. You will also get a checkpoint file. So you can place these checkpoint files by going to that folder, as many you want, and you can just from the drop down arrow. So if you just give a prompt and generate, it will generate some error because I'm not having a GPU. So I will show that. So this is my local machine, right? If you are having a GPU, you can run it now and show that. But to run this, I will not be doing in my local machine. So I will use Controlnet in a something known as Gradio interface. So it is actually not using, although I pasted it on my browser, but it is not using internet. It is on my local machine. So if I use something known as Gradio interface, this problem I won't be having. I can even run smoothly even after not having a GPU because it's online. So before I will also be starting with Controlnet. So it's 8:30 already. So I will be starting with Controlnet. Let me run this code. So in this code, what I'm trying to do is, there is a Git repository of Controlnet also, and this Automatic 1111. I'm trying to clone the Git repository, and one model I'm using, and yeah, so I'm just running this code as of now. I will explain you later. Let's just wait for 1 minute to see if outputs are proper. Yeah, so it's getting cloned. Yeah, so it's getting cloned. It will take some time. So by then, I think I should start with Controlnet. So if you just, as I said you, if you just copy paste this link on any browser, you will get this Automatic 1111 running, which would start running on the local machine. So I can go to slideshow mode now. Okay, so what is Controlnet? It is an extension to the Stable Diffusion model, as you know, that gives user an extra layer of control when it comes to image-to-image processing. So there are a lot of variants of this Controlnet. By going through those variants, you will be able to understand how exactly we are getting a control over what we are trying to produce by our Stable Diffusion model. So it's that extra layer of control when it comes to image processing. So as you can see, while converting from one image to another, you can also give some text prompts to basically enhance your image to. So I will also show you, like, one time I will just try to convert an image of, let's say, hot air balloon to another image, to some other hot air balloons, maybe some artistic ones. So that time we won't get some proper output. But if we guide our diffusion model with some prompts, that will along with the image, so that will make our results really interesting. So we will see that.
We had image to image before without Controlnet also, right?
Yeah.
So
we had that.
in Stable Diffusion, you can do image to image translation without Controlnet. But are you saying Controlnet is a more sophisticated way of controlling?
Yeah.
Okay.
So like if we want to preserve some features of the image as well as our prompts, then we can use this. And also we can by controlling how exactly it is producing output, we can even control that. So let us just see. The main idea behind Controlnet is to use additional input conditions that will tell the model exactly what to do. So with Controlnet, users can control the output to further match an original source of image. So to make it more versatile and applicable to many different use cases, Controlnet is not a standalone model, but rather an extension that can be added to any Stable Diffusion model. So the models come in two forms, blocked and trainable. So the blocked form keeps the capabilities of the production-ready diffusion models, while the trainable variant can learn new conditions for picture synthesis. So we'll just see this using a flowchart. What is this blocked and trainable thing? So yeah, what is getting preserved here? If we let's say you, or I'm assuming that you know about canny edge detection or some edge detection. Basically we use like -1,8 kernel also we can use for edge detection. So I'm assuming you know what is canny edge detection. Like if not, you can just in my advanced like in computer vision pack 2 of CellStrat, I have used this canny edge detection. So it basically detects the edges, and then we would get an output which would basically preserve a lot of data. Like the dog is looking at the same size, although it is a different dog. So that was not possible if we just put an image and we are not controlling how it is happening. The dog might get turned around or something like that. So we are getting some control over this.
So the input one is the image,
Uh-huh.
right? And the edge, that white one is the control net input.
Yeah, so basically we are specifying that go through the image to image conversion via canny edge map. So
Got it.
that's what the command we are giving.
You are passing two input images, one actual image, one that edge, the white one.
Yeah, actually this gets automatically produced from this image only.
Okay.
But we make sure that this image, in order to produce these images, these outputs, we go through this process of canny edge map.
Mm-hmm.
We are just making that. So yeah, so just overall high level in understanding of how it works. So like exact thing, it is a little difficult to explain, but I can give an overview explanation that, let's say there is a neural network block from X to Y before using Controlnet. So this was what our earlier thing. But now, so it is a neural network structure to control the stable diffusion by adding extra conditions. So we are adding some extra condition. So we are using something known as zero convolution. We are creating a locked copy and a trainable copy. And after that, we are also, like, from our initial variables, we are creating a trainable copy also. And then again, we are just merging that. And this trainable copy, we are giving instruction to this copy. And we don't have any control over the weights of the neural network, which we have initially. We have these are also the weights of the neural network, and these are also the exact copy, but we are having control over this copy, and then we are doing a convolution of those two to obtain something which we want. So I hope you get a sense of what it is exactly doing. So it copies the weights of the neural network blocks into a locked copy and a trainable copy. Both are exactly the same, just the name is different. And yeah, as the name suggests, one is locked and the other is trainable, which means that we can fine tune, or maybe we can change the weights. The trainable one learns our condition. The locked one preserves our model. So here the trainable one is learning our condition. So our condition was that go through the canny edge map. So this becomes our trainable data. Once learns your condition, and the locked one preserves your model. So thanks to this, the training with small data set of image pairs will not destroy the production ready diffusion models. So yeah, because the entire thing we are not changing. We also have this neural network block. Suppose we get some undesired output, we are not basically destroying our weights. So even if we want, like, if our trainable copy is doing something, is producing some images which we don't want, maybe we can just, we have our original weights also locked, so we can use that if we want. We are not just losing the weights, so here also it is a benefit. So thanks to this, okay, yeah. So the zero convolution is basically a 1x1 convolution with both weights and biases initialized at 0. Before training, all zero convolution output zeros, and control net will not cause any distortion. So this is before training. No layer is trained from scratch. You are still fine-tuning your original model is safe. This allows training on small scale or even personal devices.
So when you say trainable copy, what you are training actually?
So what exactly we are training is that we are just guiding this image to get converted to this image by like this trainable copy would also have some weights. Like if you want to approach this image, it also has some weights. So those weights are actually in a way shaping this image to maybe to have the same
So
posture.
what is X and Y in the trainable copy?
X and Y in the trainable copy is the input to the trainable copy is exactly like it is just a copy, just same. So one is just trainable and one is log. So we are exactly having exactly the same thing.
Input is same as X. What is Y here for trainable copy?
Okay, for trainable copy, we don't have a particular Y. We just like we just do a convolution with our fixed model, and then we get the output. Like the output of this does not it in itself does not make any meaning.
So
But
now
when
Kenny edge, where is the Kenny edge being produced?
so this Kenny edge is like this trainable copy. We are telling this trainable copy to have weights so as to approach a Kenny edge model. Like
Okay, so
we
there
are
is
actually
the
producing that Kenny edge image.
Okay, trainable copy has the goal to achieve
It has the weights. It has the weights actually.
Okay.
So we are doing convolution of those weights with our original neural network. So like we are actually not producing that. We can, I think, produce this Kenny edge also, but we have the weights for that.
Now I have a feeling that C is the Kenny edge. That C at the top right. That probably is that C. That has some significance. That is the one being fed here, and to that you are adding the original X with using the plus sign.
So this C is basically our command. Hello.
This is control logic.
So this is our command that through what path I need to go. Like there can be many other paths also. Instead of Kenny edge, we can follow a path of maybe pose, or
Right.
maybe depth, or maybe semantic.
Correct.
So this is our command to.
This is only a conceptual diagram actually.
Yeah.
This is not actually the architecture of the control net with SD.
Yeah.
This is just conceptual explanation.
So actually, this, like as we know that this is not just a single neural network. It means from this X to Y also there is forward process, then backward process, then unit, and then all those positional timestamp, everything is happening. Okay. So yeah. So I will just go quickly and see whether the code is running properly. If some problem there, then I may need to correct that.
Yeah, so Mitadru, one question. So here the text is basically the text prompt and the dog image is basically the control, or the other way around. So which is the control here? Is a dog image?
No. Just a second. Here the input is our dog image, and the control is that I want to produce a Kenny edge map out of this dog image, and the Kenny edge map of this image of our dog image should be similar to our output. That is basically the control. Like we are not
so
creating
in a regular text to image stable diffusion, we give a text prompt and that creates an image, right?
Yeah.
So now, and that doesn't have any control, like so it will create most probably like a creative
Yeah.
state, like which we do not have control. So it's probably there is a lot of stochasticity in that. So now we want to put more control on it, and that control is driven by this dog image. That's what is correct, right?
So just a second. If we just input this dog image in a, let's say, image to image classifier, classifier I'm telling, image to image SD model. So what can happen? Like a dog, we will get another dog, but that may be playing with something or maybe some other position, maybe like that. But when we say that use this input image, but go through the canny edge map of this, and then produce the output. So the canny edge map is there. We are not using any text prompt.
Example here, you say prompt is equal is a cute dog. That is a text prompt, right?
Yeah.
Or control stable diffusion with canny edge maps. That is a text prompt. Which is the text prompt here? Like the cute dog, I suppose.
So this is telling that prompt this. If we give a prompt of cute dog, it produces this image. Let's say.
Okay.
And then there are options to select. This is basically an image to image with an option of going through the canny edge map.
Okay, cool.
So we are selecting the option, just say go through the canny edge. This
I think the mechanics of how canny edge control is passed is not shown here, I feel. So it's a cute dog. The dog is the input image, but how the canny edge is specified, whether it's a text to specify canny edge control or is it image of that canny edge? That
image actually.
This is not explained here, Bismillah, I feel. So there is more to it, how the control logic is being passed in.
So like if you give me like 5 minutes of time, now I can explain like how exactly this canny edge is working, but that will be a little bit off topic. So should I do that?
No issues. You can continue. We'll discuss offline if you want.
Okay. So actually there is a filter known as -1,8 filter. So if we pass that filter through the pixels of this, so that kernel filter will go through all the pixels of this, and that in a way can find out the edges of that. So that's how it works actually. So I guess there is some issue here.
Okay, you can explain code on a high level, even if it's not running.
Yeah, so no, the output has.
See, this does seem similar to conditional GAN. We used to do CGAN or image to image, GAN. So it seems similar to that. But the control logic is more sophisticated. In conditional CGAN or image to image GAN, you could not control much. But here there is some more sophisticated control logic.
Yeah. Even if it does not run, it was running. I can explain you what exactly happened. So let us just proceed.
Yeah, you can ignore the running aspect.
Like the output won't come actually. There will be a link. Till this much it is okay. So let us just see the other variation. So so the exact working, so this there was a blocked copy and a trainable copy. So here the same thing is done, but it is expanded. So this entire thing is the log copy here, which consists of that encoder, decoder and all. And the typical blocks which are used in SD. And this trainable copy also has the same SD encoder block and all. So yeah, you can see. So after like each trainable copy, we are just doing convolution and giving input to the decoder block actually. So this thing is not detailed yet. We are doing convolution of the the encoder portion of our weights is same in the trainable copy, and then we are doing zero convolution with basically the decoder block, and then we are getting the output.
Yeah,
So
actually,
this
zero convolution is just a one-by-one convolution. The sole purpose of that
yeah
is to change the depth perception. So you can actually add it to
yeah
the thing on the left. So zero convolution has no other purpose but to change the depth perception. So it will become a compatible, addable matrix.
yes
You are adding that to the left at different steps.
yes. So in this way, the control net can reuse the SD encoder as a really strong and robust and powerful backbone to learn the diverse controls. So many evidences validate that SD encoder is an excellent backbone here. And note that the way we connect the layers is computationally efficient. The original SD encoder does not need to store gradients. The locked original SD encoder and the required GPU memory is not much larger than the original SD. So basically it is telling that like we are doing the parallel processing here basically. So the required GPU memory is not much larger, but obviously greater, although many layers are added. So yeah. So I've just repeated the slide. This was a variant one. So what we can do is there is also something known as hook lines map. So there is an algorithm known as hook lines transformation algorithm. So using that, we can get the lines. So here we are not getting all the edges, but the lines we are trying to preserve that, and you can see the output also has the same hook lines map. So there is also an algorithm to generate this hook lines transformation. So this thing is also there in that computer vision pack too.
This is
So
nice. So I can develop an interior design solution for
yeah,
for houses and buildings, right?
yes,
So we can develop a full stack interior design or a building design solution, correct?
yeah, and on doing so, like we have a better control also. Like we want something to be like this of this architecture, but different design. We can have that.
Right.
Earlier, if we used to give only this image, it can maybe totally change the thing.
So Mitadru, later on, I am going to ask you for our SD product, we want to start conditioning it for specific business use case. So what would be a high impact use case? But that is a longer discussion. We can have it offline because we are
Yeah,
going to
sure.
relaunch our SD product with your help.
Okay, sure. So again, this I told you that this hook lines map can also be produced with something known as hook lines transformation, and this again there is something known as HED maps, which does something better than canny edge detection. It is also an edge detection more or less, but you can see that it is something holistically nested edge detection. It attempts to address the limitations of canny edge detector through an end-to-end deep neural network. So this network accepts an RGB image as an input and then produces an edge map as the output. So even to convert from the picture to the edge also we are using a neural network, and in canny edge detection to convert a picture to the map we are just using one kernel filter. So furthermore, the edge map produced by HED does a better job at preserving the object boundaries in the image. So if you try to detect the edge of this, you might get a lot of edges which are irrelevant, but here we get a fine edge which basically preserves the structure. So this edge detection method, HED edge detection method, is also useful to add another layer of control maybe. And so there was something also scribble map. So this scribble map is nothing special. We are just drawing this with our own hands, and like whatever we want, we are just telling what shape it should be or something like. This is not much help. Like it is a normal text to image, we can say, but using Controlnet, I think just it is using SD, I guess 2.0 or something. So it's just better. So suppose we have a pose. Let's say we have this human pose, and we do pose detection of that. And then suppose we want a chef to be in the same pose as this. So here comes the prompts also. So if I tell, so here the prompt and the image both acts as an input. So and we are also, so here we are giving two layer of control. One control is that I am telling I want a chef through my prompt. Another layer of control is that I am telling it should have the same pose as this. Go through the pose detection. So we get a chef who is in the same pose as this. So we have an extra layer of control here.
If you didn't give pause, it will turn around the person in unpredictable ways, correct?
Yeah. Yes.
Okay. Very interesting. This is amazing.
Yes. So like a lot, like through all these variants, we can like control to a lot of extent. I think like, we can try out some cool things. I will try those later. So let's say prompt is just a house which produces this, and so I here what I'm doing is that I am preserving the semantic structure of our data and getting a new design of the house. So this conversion is known as semantic segmentation. It can be done something like we can use the pre-trained networks for this creation using a library known as gluon-CV. So it is a library after OpenCV, like it is launched by Facebook, and in that computer vision pack again you will get this semantic segmentation. You can go using a module known as gluon-CV. You can just convert this to this. So it also uses pre-trained weights for this conversion, and we get something semantic segmentation. And then by preserving the semantic structure of the data to a greater extent, we can just create a new design of a house. So again, there are different types of controls here. There are depth maps for that. So we can like, so this gives another layer of control. Like not only the maps, not only the like earlier what we were doing in this same image, we were doing hook lines maps, right? So it just preserves the lines. So here we want to preserve the depth also. So the inside will be darker, or there will be better outputs.
So did you see a situation where they combine two different controls? Let's say I want to combine hook line map with depth map. Possible?
So this interface is taking only one input.
This UI you got somewhere, huh? It's already there.
Yeah, this like that GitHub code of Automatic1111 and Controlnet, like they have this
Already the UI exists.
Understood.
Okay.
So that UI is hard coded completely because we are just cloning and using that.
Understood.
So there is also something known as normal maps, and it performs better than depth maps, which shown to have performed better than depth maps. So I also got in this source, I also got something known as depth versus normal maps. So it could have produced like it could have shown that if in this same image we are applying depth map, then we are not getting this much good results. So using normal maps we can do that. So I was trying to do this. So yesterday I was doing this. Let's see. Okay. So in this account, so it is basically similar to this. What I'm telling. This batch file we ran, and we just copy pasted this link. If we run this code, we were supposed to get a similar link, and if we click that link, then an interface will open which is known as Gradio interface, and that is not our local interface which needs GPU. So even without GPU that was working. So I will try that out. So yeah. So some different account. Same thing if I try in some different account, I think it should work. So let me uncomment this.
Yeah, it's all right. I think running code is not so important. You know that that demonstration of those use cases is very interesting.
Yeah, like if this code ran like we would have got this some link similar to this, and then like I could have actually showed you what I was presenting. Like we could have ran an actual system. So it's already 9:06 and we have the Dreambooth also. So I will go ahead and hope this actually runs.
Yeah, one question, Mitadru, like to use this Controlnet, it just works out of the box, right? Or do we need to fine tune it for different custom domains? Because I believe that it is sort of generic pipeline.
Yeah,
Means-
yeah.
So you give the text prompt, you just give some control factors like the dog image and all those things.
Yes, yes.
And it should take and work, right? We don't have to fine tune this control net for different domains. Does that
No.
is
Yeah, so one fine tuning using Controlnet, I am yet to explore that. In actually in image inpainting, we can let's say fine tune. Suppose we have a like I was going through one problem. We have let's say a room where we want to a blank room where we want to generate some furniture. Those furniture will be AI generated. So that's basically in painting. So that was also I guess was using Controlnet, and it was every time preserving the background more or less. So that was they were calling fine tuning, but I'm like yet to discover. So as of now here there is no fine tuning.
okay?
in Dreambooth I can show how control happens.
So if somebody was using Delhi 2, these Controlnet Dreambooth work on Delhi 2, or they are only specific to SD?
Delhi 2 is like completely for open AIs. So like we are using SDA.
Okay.
We
no,
don't know that.
Okay, we don't know how to if these work with Delhi. Okay.
I wanted to show this. So you can like I'm giving this thing. You can run this. It would run for sure. This Colab notebook. You have to just run this, and then just click on a link which will appear running on public host something. The link will appear something like this, and you can just try out the things which I was telling throughout the presentation of control. You can just try those out by uploading images and giving some control. So should I also start with Dreambooth? I think concept I can give.
Yeah, you can just do a brief intro.
Uh,
Yeah, that should be fine.
so this is basically a personalized stable diffusion. So we would not directly jump into the definition of this because like when I first tried to read this, like I couldn't means differentiate with a normal stable diffusion. But to differentiate this, I would suggest that we should go through a story first. So let's say, so we need to exactly realize why Dreambooth, why such an extension. So one big issue with large language models is repeatability, or in other words, controlling the subject's appearance and identity using text is very hard. So what it is actually saying. So let's say we are creating images for a story. So at the start of today's webinar, I told you that like maybe we can have an entire film whose characters are made by stable diffusion. So that can make a movie. So let's say we have a short story, a knight who fights a dragon and then befriends it. So we want 3 images for this small story. Let's say a knight, and then another image where knight is fighting a dragon, and then another image where the knight is riding the dragon. Befriends the dragon. So let's say how we can achieve that. If we try to generate this image by using some very intelligent prompt, let's say we are using some prompt like highly detailed VFX portrait of a brave and noble knight. So let's say we get this knight. So this becomes our character of our story. So that in our story, this knight is fighting a dragon, and then it just rides on that dragon. So at first, using a very intelligent prompts, we get a really nice character of knight. So then for when we go to do the remaining 2, let's say also by using 2 other very intelligent prompts, we are making images for our knight to fight a dragon and riding on the dragon respectively, right? So here our knight is fighting the dragon, and here it is riding on the dragon. So let's see what is the error with this. Let's have a close look to this. So we observe like our character of the story can't get changed, right? Here our knight is wearing a helmet and it is riding on a horse which looks like this, and you see that it is not, suddenly it is not wearing any helmet, and the armor have also changed a little bit, and yeah, so some things have changed. And this is the third picture where it is befriending the dragon. That is even more disastrous. If you notice this, this knight has got mixed with the dragon, the body of the knight, and the head is also not properly visible. And to ensure you that like we have used like really intelligent prompts to do this, some prompts like this which are not wrong. So we are not going wrong in our prompt engineering, and we are trying to produce a story. So that also might create a lot of mess. So we are not able to basically preserve the identity of this knight or the identity of this dragon. Sometimes even horrific things are happening, like the knight and the dragon is getting mixed. So here is the need for our Dreambooth. So 3 prompts for a knight, let's say 3 completely different knights. This also might be possible. The problem is worse with object without a recognizable major trait like an armor. So how we can create art with a specific likeliness? So and what if we want to make the art and the images with the likeness of someone we actually know? So let's say we want to tell a story about myself. So every time my face cannot get changed. So we need to preserve this. We need to find something to preserve this personal means personal things like so we also known as Dreambooth is also known as personalized stable diffusion.
So is it for creating stories like this, story books, or there is more uses?
So we can like what we can do is we can let's say input what demo I was going to show today actually was we have a code and we are inputting let's say 5 to 6 or maybe 20 pictures of ourselves, and then the model is fine tuning with our pictures, and it is getting to know how I actually look. But that would take a lot of time to run the code, but I would show the process for sure. So this use is also there. So anywhere where we are like just we are just hoping to preserve the identity of the character or preserve the the exact face, we can say. So we can use Dreambooth there. And okay, so the Dreambooth allows us to take our own images and train the AI to recognize an object, person, image, or it may be an image or thing. So Dreambooth was first created by Google researchers. So from their official website, I have taken this explanations. So this is a personalized stable diffusion. It is a tool to fine-tune an existing text-to-image model like stable diffusion using only a few of our own images. So it means that we can customize the AI model so that it can make an infinite number of variations of you, your dog, or let's say your car. So here is an interesting example. These are our input images. So and now let's say we give a prompt to this. Let's say our input image is in Acropolis. So see that the model has learned how the character looks like, how our input images looks like, and it is not destroying that. Even if it has to bend, let's say, the ears for the swimming, and let's say it has to change the pose completely while sleeping, or it is in a bucket, or let's say getting a haircut even. So it is not destroying the information of the data. So like we can make a dog story with this. So, yeah.
No, so again, I'm thinking, is it for primarily for storybook creation?
Storybook creation maybe, and for let's say for film, and for fine tuning, and basically if we want to preserve some information on any of the applications, like the one of the application is sort for storybook, movie building, and stuff. Like we might also be able to think some other users.
So let's say I am into the business of space. So I
Yeah.
want to, or maybe I'm into cars. So I want to do, I want to train stable diffusion for car design. So the basic stable diffusion will produce generic cars. Maybe I want to train them on my kind of cars. So that's where Dreambooth will be useful.
Yeah, that's also.
So custom corpus.
Yes.
So it
For
always
custom.
train on custom corpus of images.
Yeah.
Okay. Otherwise, it will produce generic images which may go away from my custom corpus. Okay. Got it.
So, okay. So this is taken from that Google website. So Dreambooth is basically created entirely by Google, it seems. So there was some github.io. So basically it is taking, it claims to take only 3 to 5 images, but a place where I was reading, it was told that it would take 20 input images to learn the subject. So Google claims that it can learn the subject by using only 3 to 5 images. And let's say we have a text to image model and an input model. We are fine tuning it with Dreambooth, and our output, let's say we have a unique character, and we overall what we are having is a personalized text to image. So if we tell that this, our subject dog is in the beach. So this dog is in the beach. So we have a stable diffusion model which is completely personalized. So this, we have our subject dog which is working on a colorful carpet. So yeah, we have that. So the corresponding class names and returns a fine-tuned personalized text to image diffusion model that encodes a unique identifier that refers to the subject. Then at inference, we can implant the unique identifier in different sentences to synthesize the subjects in different contexts. So there is a
Can you explain this architecture again?
Yeah. This one.
Yeah, maybe this one.
So I'm using the reference here. So here we have a text to image classifier also. What this text to image is doing, let's say we are giving text like getting a haircut or in a bucket. These are the text. So this text to image and also this input image, using some kind of fine tuning, we are producing an output. We are producing a tool, a model which is completely personalized. Like it is like we are giving text, like once we feed the inputs, so these are known as concept images. Once we feed the concept images, we are actually to produce this image to produce these any images which is being shown in the right. We are just giving a prompt, right? In the Acropolis, swimming, sleeping in a doghouse, given that our subjects look like this. So this is basically a text to image. So that text to image is here. And we also have some input images which learns the concept using Dreambooth. So overall what we are getting is a personalized text to image classifier.
What is that V?
So it uniquely identifies the subject. So let's say V is a unique identifier which has the information of this subject. So
this kind of sounds like control logic as well. So you are training like control logic.
Yeah. So in Controlnet, so we can do comparison with Controlnet also. Let's say we are using Controlnet, let's say canny edge of this dog. Then the structure of the dog will remain same, but the personal thing, like the further details of the dog, might change.
It will not be similar to the kind of dogs I wanted.
Like got it. The same dog.
Yeah.
But maybe the pose and the edge will be same. But here if you see, the pose is also getting changed. Like many things are getting changed, but still the subject is same. So it basically learns the subject separately.
So let's say I wanted to train, create fashion models with my set of fashion clothing. What would be the appropriate architecture selection? a choice. So I am a fashion designer. I have been making certain, fashion clothing. I want to overlay that on fictitious, models. So how will I do it? Will I use Dreambooth or Controlnet or something else?
So if you have a model image and you are basically trying to make that model wear clothes, so that should fall in inpainting. And
No, I have my own clothing, and I'm
okay,
okay with creating fictitious or fake models. And those fictitious models, so I'll say a white, teenager girl walking on the beach wearing my
yes, here,
gown. The gown is mine, but
yeah.
that
So here Dreambooth.
okay, Dreambooth, okay.
Yeah, because our concept images is our model, our design.
Our
So
design, not our model. Model is generated fake.
so yeah, so the design is here the thing which we are learning as a subject. So that design is every time getting preserved with new kinds of model. Yeah, that's also.
So my clothing is preserved, let's say gown or dress or shirt or trousers.
Yeah,
So that should be preserved,
yeah,
but it should overlay on fictitious mannequins
yeah,
on models. So
yeah.
is Dreambooth situation, huh?
So like the input concept images will be of that clothing. So it will learn the clothing to make it fit.
Got it.
And like in a way it also somehow understand the subject. Let's say uh, during the time of training we are only giving this subject, let's say this dog, that time it learns only the structure of the dog, but in some way it is also learning that getting haircut. So getting haircut means what it knows that uh, we have to use a scissor and a hand, but like it is in an exact place. I mean, this scissor could have been also somewhere here, which is not in the dog. So it also has some relation with our, like, the prompt is also having some relation that how exactly hair cutting is done. So how that is done, maybe I have to search that out. So maybe that is hidden in the details of this classifier or. Yeah. So given 3 to 5 images of a subject, we fine-tune a text-to-image diffusion model in 2 steps, fine-tuning the low-resolution text-to-image models with the input images paired with a text prompt containing unique identifier and the name of the class the subject belongs to. Let's say photo of a T dog. T is our personalized dog. In parallel, we apply a class-specific prior preservation loss. So, okay. So it, like in a very overview way, it is trying to explain what exactly is the loss. So uh, as we go to the forward process, we get a noisy image, and then we are just reconstructing our image. In the process of doing so, we are giving a loss. We are also setting some loss by which, like, if the image is different from like the more the subject is different from output subject is different from the input subject's features, those features they are learning, and more these features are different, we are giving some loss. So there is some reconstruction loss. So we apply some class specific prior preservation loss. So it is preserving, so it basically learns the features of these images and then detailed features, and then it just applies some prior preservation loss, which actually makes this possible. So yeah, that's all, I guess. The overall concept I had this.
Okay, good stuff. What more, Mitadru? You have the code demo. Okay.
Yeah, for Dreambooth also I'm having, but this code takes even longer.
Yeah, I think we can take it up later. What do you say?
Yeah, maybe later I will make these two prepared. So, what exactly is the step-by-step procedure for what exactly do we need to do in the code? That is also a step-by-step procedure. So maybe we can discuss that. Meanwhile, you can just run this. This fast so Dreambooth is like a really computationally expensive. So even this fast Dreambooth model would take around 90 minutes to run. Giving you the notebook, you can just go through that. The instruction are written sidewise. Like you will, so to run this code, you will be actually needing uh, the access for the contents of Google Drive. So actually the checkpoint files are really large. So here there was a ready-made checkpoint files. So in Dreambooth, using the concept images, it is creating the checkpoint files and saving that in Google Drive. So it's working that way. So just let me show you one thing. Like after running the code, what you will see is you will get a folder like this, Fast Dreambooth, that you will in the session. Not this. In this session, you will get the checkpoint files here. So these checkpoint files you can utilize. This basically contains the trained weights of the Dreambooth. So you can use these checkpoint files to paste this here in the checkpoint. Here also in the model portion, in the models table diffusion, you can place the checkpoint files here and just run it. That should do the work. So yeah, that's all.
Okay, excellent session. Audience, any final questions? So the lot of advanced stuff in a compressed time format. So, but well explained by Mitadru. We got a lot of ideas here. Any final comments, audience? Okay, so Mitadru, thanks for that. We'll
Thank
look
you, sir.
to next set of sessions. There's a lot to deep dive again.
Yeah,
Thanks for this session. Nice.
thanks a lot.